Hello, hi everyone. Welcome to Lab 3. So this is going to be a short video because most of the content which we've covered in this notebook, which you'll find in the Medium article of the lecture 7 titled GPU and CUDA programming. So if you scroll down, most of the things which I've covered in the lecture are from this notebook itself. So in the Lab 3, you're expected to actually follow this notebook. And more than that, there is an optional bonus section like this. The part is complicated, so I did not cover it in the lecture, but and this one is about making a neural network in CUDA based on a blog post which we've just copied here. So here the complete code is trained on C++ for running machine learning model, and it is being executed in the GPU. So how those files are written and are compiled together, that is the main part. So let's just quickly go through this notebook, and I want you to follow along with the lecture as well as separately in the lab session. So here we're just installing the NVCC, which is the NVIDIA CUDA compiler for Jupyter, and we're loading that extension, and anytime we type %% CUDA, it is referring to that extension, and we're just printing the hello world. So you've seen all this, that what these two things indicate, the blocks and the number of threads, and we've continued the experimentation with that and how it can be classified into groups of 3, like can have a dimension of 3. Then we saw the use of the CUDA random library, CURAN library, and how we can generate random numbers with that by calling the APIs mentioned in this library. So you see that we're trying to generate some random numbers. Then we saw the communication between the host and the device, that how the memory is allocated on the GPU and how we can copy it from host to device and then later on from device to host to again print it. We saw a task on parallelizing a CPU task on GPU. So first we saw how much time it took on the CPU, and then once we parallelized it on the GPU, how much time it was taking. And then we saw how we can actually compile many of these things together and how we can profile and figure out which operation is taking the most number of time and which API call is actually happening is again taking most number of time, and the GPU activity wise which GPU function is taking the max time. So there is also a task which is mentioned. The solution for that task is presented here. I would highly recommend to actually try that out before you see the results. And finally, the machine learning complete thing is presented. So here it's like some classes we have defined, like just to give an example that how the whole compilation thing will take place. So we've compiled some class.hh file, like we've written this to the header file, and then we've tried to fill that information with some class.cu file, and we've written a main.cu file, and if we compile all of this together, some class.cu or main.cu file, and here we've included the header file here itself, so it will compile all these things together and will give an output file. So if we just execute this output file, we'll see that it works, will get printed. So this is how the compilation happens. We can also define some helper functions, structures and classes. So we're defining shape.hh file and shape.cu file. Here we're creating a shape. So you'll see that if we execute this file by passing shape 100, 200 and then calling out this, like we create using this structure, then the final things which you're wanting to print using shape.y and shape.x, they get printed. We're also looking at exceptional handling here and seeing that the operations get completed without throwing any error. We are defining the matrix class which abstracts some of the communication between the device and the host, allowing matrix of values to be easily passed between the memory locations. So it will allow for memory to be allocated on the GPU for the matrix, memory to be allocated on the CPU for the matrix. Memory to be allocated on both the CPU and GPU for the matrix. Allocate memory if it is already if it isn't allocated already, and copy data and from device to host, host to device. So there are certain helper functions which will help us do that. Then we're defining how to calculate the binary cross entropy loss function, which we'll be using in our machine learning model as the loss function. And we just calculated it for predefined set of values, and these are the results. We're defining the layers, the neural network layers, the linear layer, and we're defining a main function to help us compile all this matrix, shape, binary cross entropy, linear layer, and output them together. So it's just a single forward pass which we're seeing here, and we can also train it by doing the back propagation. So along with that, we have a sigmoid function which we're defining for introducing non-linearity into the system and making ReLU activations. And finally, so once we have done the utilities for abstractions to handling matrices, abstraction for handling errors, a handy little structure for defining shape. So now we'll just actually run the neural network with all the data set and the back propagation, and we'll print out the results. So this is how the training has performed by achieving an accuracy of close to 90% with consistently over the epochs the loss function is decreasing. So you can try this out. The last part is a little complicated, but before that you can attempt in your lab 3. Thank you so much.